Welcome, curious minds, to another deep dive. Today we're embarking on an expansive exploration into the very essence of how we build our world, but not just the bricks and mortar. We're going to uncover the hidden intelligence that shapes everything from a single, carefully chosen beam to the sprawling, interconnected fabric of an entire smart city. How do we bridge the gap between ancient wisdom and cutting-edge technology, between raw materials and sustainable metropolises, and maybe most importantly, between human vision and the physical reality we inhabit?
Indeed. And we've gathered a truly fascinating stack of sources for you today. Everything from practical guides on building information modeling and project management standards to detailed insights into building science and codes, historical architectural treatises, and even some compelling philosophical perspectives on engineering, sustainability, and, well, the future of urban systems.
Yeah, quite a mix.
It's a rich tapestry of knowledge waiting to be unraveled, and our mission, I suppose, is to connect these seemingly disparate threads into a coherent, compelling narrative.
Right. Our mission today is to unpack these diverse perspectives, extracting the crucial insights that illuminate the intricate world of construction and design. You'll discover how age-old principles still apply, how cutting-edge technology is, well, revolutionizing the field, and why understanding the how and why of building is more important than ever. What stands out to you as we prepare to jump in, before we even touch the blueprint?
What's really fascinating here is the sheer breadth of considerations that go into creating our built environment. It's not just about, erecting structures. It's about meticulous planning, ethical considerations, the quiet responsibility, maybe, of shaping our shared spaces and a constant evolution of knowledge. We'll connect the dots between seemingly disparate ideas, illustrating how everything is interconnected, from a single joist, really, to a comprehensive urban plan. It's a journey of understanding the profound interplay between materials, human ingenuity, and the environment.
Okay, let's unpack this with some foundational knowledge. Materials and how buildings actually stand up and perform. What are the core considerations, and how do ancient insights still, inform modern practice? Because before anything else, a building needs to stand on solid ground, right?
Exactly. And this raises an important question. What defines good construction? Especially when we look at the very basic elements that make a structure enduring. Our sources highlight that every building, regardless of its size, requires a foundation meticulously adapted to its loads and the specific ground conditions. Sometimes this means penetrating 100 feet, that's 30 meters or more below the surface.
Wow, 100 feet.
Yeah. The real insight here is that the ground isn't just a passive support. It's an active and sometimes challenging participant in the structural system. Understanding its temperament is the very first step.
That's incredible. So the ground beneath our feet is just as important as the structure above it. It's literally the first silent partner in any build. But what about the actual stuff we build with? Did early thinkers have any enduring insights into that?
Oh, absolutely. The wisdom of materials is truly timeless and often surprisingly scientific. For instance, Leon Battista Alberti, writing way back in the Architecture in 10 books, offers some profound advice on material selection that resonates even today. He didn't just say, don't use weak wood. He specifically notes that certain woods, like olive, fig, or linden, are simply unfit for beams. Why?
Why?
Because they break into shivers, then to split. This isn't just an observation, it's a critical warning based on how the material's grain behaves under structural stress. It's a truly empirical approach for his time.
That's incredible foresight, identifying the why behind material failure centuries ago, so he knew what to avoid. What materials did he champion for their strength and resilience?
Well, conversely, Alberti highly commends juniper for its durability when exposed to open air, even drawing a comparison to cedar. And he esteems boxwood as one of the best of all. This ancient attention to a material's inherent properties, its grain, its resilience, its behavior in specific environmental conditions, remains absolutely paramount for structural integrity. It's the foundational understanding that dictates not just what can be built, but what should be built for longevity.
It's amazing how those ancient insights still hold true. Moving to more modern building blocks, what does contemporary practice tell us about materials like, say, concrete and masonry? How do we ensure these relatively common materials perform under immense stress?
Right, bringing it forward, Building Codes Illustrated provides crucial, detailed insights into concrete and masonry, basically formalizing centuries of learning. For concrete, structural elements like beams, girders, and floor systems are often placed monolithically, meaning they're cast as a single continuous unit. The real insight here is how this seemingly simple technique allows us to transform a loose aggregate into a seamless, incredibly strong skin that can bear immense loads.
Yeah.
It effectively blurs the lines between individual components and the entire structural system. And columns, which bear a huge amount of weight, they must have specialized reinforcement to prevent them from buckling, right? What are the key engineering challenges there?
That's right. Columns, primarily supporting axial compressive loads, require careful lateral reinforcement. That could be through continuously wound spiral reinforcement or specific ties. This isn't just about the concrete itself, but how it's engineered to resist buckling and shear forces, ensuring it acts as a unified, strong unit.
Hmm.
Similarly, for masonry, the allowable compressive stresses in walls vary significantly. This isn't just one number.
It depends. It depends heavily on factors like the specific type of mortar used. Some are much stronger than others, and the composition of the unit itself, whether it's solid brick, hollow concrete, or natural stone. It's a nuanced calculation, emphasizing that masonry isn't a one-size-fits-all solution, but a highly engineered system.
So, the type of mortar makes a huge difference in how much stress a wall can take. Are there particular regions where these requirements become even more stringent, forcing even greater precision?
Absolutely. The text emphasizes that more stringent requirements apply for seismic zones 3 and 4.
Earthquake zones.
Exactly. Areas prone to significant earthquake activity. This underscores the vital role of a professional engineer in design and construction, and the absolute necessity of adherence to the building code for ensuring structural integrity and public safety in specific geographic contexts. It's about building in a way that respects, well, the power of nature.
You can see how this meticulous understanding of what materials are best suited for what purpose and how they behave under stress is not just academic. It directly impacts the longevity and safety of the very spaces you inhabit every day. It's the invisible scaffolding of science and careful thought. Now, let's delve into the more intricate details of construction, especially concerning environmental performance and climate adaptation. It seems like the internal environment of a building is just as complex as its external one, and getting that right is crucial for comfort and durability.
If we connect this to the bigger picture of how buildings interact with their specific environments, the Builder's Guide to Hot, Dry, and Mixed Dry Climates delves into critical aspects like air and vapor management. These are essential for long-term performance. This isn't just about comfort, really. It's about the very health of the building.
I've heard about vapor barriers. Are they always a good idea, or does it depend on the climate? Because sometimes what sounds logical can actually, well, backfire.
Yeah, this is a nuanced area where generalized solutions can actually create significant problems. The guide explicitly states that polyethylene, standard plastic sheeting, is not recommended as an interior air barrier for many climates. Cold, mixed humid, marine, mixed dry, or hot humid.
Why not? Seems counterintuitive.
The reason is its impermeability. It basically stops vapor dead in its tracks, which can unfortunately trap moisture within the wall assembly. Imagine putting on a non-breathable raincoat inside your house. The trapped moisture can lead to issues like mold, rot, and ultimately structural damage.
Yikes. Okay, so what are the preferred alternatives for air barriers in those climates if polyethylene isn't suitable? It sounds like you need something that controls air without, suffocating the wall.
Precisely. Preferred approaches include meticulously sealing drywall to top and bottom plates with caulk or gaskets, or ensuring exterior sheathing has taped and sealed joints. The key is to control air movement without trapping vapor. Understanding the vapor profile, which involves allowing drying to both the exterior and interior in mixed dry climates, is also crucial.
Drying both ways.
Yes, for selecting appropriate insulation, like unfaced fiberglass cavity insulation, which allows this bidirectional drying. It's about letting the building breathe in a controlled and intelligent way.
That makes perfect sense, letting the building breathe in a controlled way. What about specialized roofing and insulation specific to different climates? Do roofs have their own unique moisture challenges?
Oh, they absolutely do. For roofs, particularly in hot, humid, mixed humid, and marine climates, vented roof assemblies should generally be avoided.
Avoided. I thought venting was good.
Not always in those climates. This is due to what's known as inward vapor drive from incident solar radiation. Essentially, the sun heats the roof intensely, driving moisture from the exterior inwards, which can then get trapped underneath. To control this, a carefully selected low-permeability vapor retarder is essential under asphalt roofing shingles.
Oh.
However, if you're using wood shingles or shakes, a minimum 14-inch vented airspace is actually required between them and the roofing felt for similar reasons of moisture management, but it lets any trapped moisture escape outwards. So it really depends on the material.
It sounds like insulation isn't just about keeping heat in or out, but also fundamentally about managing moisture. Every single layer has to be chosen for its specific role in that complex moisture dance.
Precisely. Insulation strategies vary widely based on these moisture and thermal considerations. For instance, rigid foam plastic on exterior foundation walls requires careful consideration for issues like termite infestation and fire protection, which can become hidden liabilities.
Right, termites love foam.
They can, yes. In heated crawl spaces, batt insulation is common, while rigid insulation can be placed under floor joists to reduce thermal bridging. That's where heat is scaled through structural elements and protect against humidity. Each choice is a calculated response to a specific climate and structural context, ensuring the building performs as intended over decades.
And these meticulous details even extend to how windows and slabs are installed. It sounds like every tiny junction needs this level of engineering thought.
Absolutely. The sources provide specific construction methods, for instance, for ICF, that's insulated concrete form, recessed window jambs within stucco walls. This type of detail emphasizes that windows are installed before the stucco, with sealant carefully applied to the window flange, a precise sequencing to prevent leaks.
Ah, the order matters.
Immensely. For garage slabs, which are often exposed to ground moisture and potential contaminants, a polyethylene vapor barrier is essential under the slab, along with a 4-inch granular capillary break and a drainage pad. These detailed examples underscore the complex interplay of materials, design, and climate adaptation, ensuring not just durability, but also a healthy, resilient environment within the structure.
It sounds like every single element has a specific role, and building codes are absolutely essential for ensuring everything works together safely and efficiently. There's a formal science to all this, which is constantly evolving.
Absolutely. Building Codes Illustrated and Fundamentals of Building Construction provide the critical framework for these requirements, from fire safety to structural loading. They basically formalize the art of building into a science. These aren't just suggestions. They're the bedrock of safe construction, distillations of countless lessons learned, often tragically, over centuries.
So how do these codes categorize buildings, and what does that mean for designers and builders when they're first envisioning a project?
A core aspect is the International Building Code, IBC's definition of occupancy classifications. For example, Group A occupancies are typically for 50 or more occupants engaged in civic, social, religious functions, recreation, or food and drink consumption, think theaters or restaurants.
Okay, larger gatherings.
Right. In contrast, assembly areas with fewer than 50 occupants or business occupancies like offices are classified as Group B. These classifications are crucial because they dictate fundamental design parameters, from the required number of exits to the fire suppression systems needed. They essentially define the baseline for safety based on how a building will be used.
I understand that codes often have rules about fire resistance. Can you make trade-offs between, say, sprinklers and fire-rated walls? Because that sounds like an area where smart design choices could save both lives and money.
The code does recognize the efficacy of trade-offs between construction types and fire protection methods, but it's a careful balance. The critical insight here is that active systems like sprinklers generally cannot be used to offset passive fire resistance requirements if those active systems are already code mandated to increase allowable building heights in areas.
Ah, so you can't double count the benefit.
Exactly. The idea of a trade-off implies a voluntary selection. But if the code already requires sprinklers for basic safety or to achieve a certain building size, they can't then also count as a trade-off for other passive measures. You can't double dip, so to speak, on fundamental safety.
That makes sense. So basic fire safety is non-negotiable, and then you can add on. What other specific fire safety measures are detailed in the codes to prevent the spread of fire and smoke?
Well, specific requirements for smoke barriers highlight the meticulous detail of these regulations. Smoke barriers need to be continuous through concealed spaces, like above ceilings, unless they directly abut fire-rated assemblies. So no gaps for smoke. Precisely. We're talking about precise construction that prevents smoke migration, which is often a bigger killer than fire itself. Similarly, shaft enclosures, such as those for refuse and laundry chutes, require 1-hour rated access rooms on each floor and 1-hour rated termination rooms at the bottom, alongside active fire protection systems. This level of detail ensures that even service shafts, which can span many floors, are compartmentalized for safety, preventing them from becoming chimneys for fire or smoke.
Fascinating. So the codes don't just focus on the components, but also on how everything behaves at different scales, from a single column to an entire building.
This is where structures, or why things don't fall down, offers a really crucial insight. It states that while small components like bolts and crankshafts can safely use high-strength metals and high working stresses, the larger the structure, think of massive ships and bridges, the lower the stress that may have to be accepted in the interests of safety.
Lower stress for bigger things. That seems backwards.
It does seem counterintuitive, but it's a fundamental principle of structural engineering. It demonstrates how the sheer scale of a project profoundly influences material choices and design approaches. Engineers have to be more conservative as structures grow larger because the consequences of failure are just exponentially greater.
That's a powerful point about scale. And bringing it back to everyday experience, how do building codes and principles influence something as fundamental as natural light in a room? Because light isn't just aesthetic, it impacts our well-being.
Right. Building Construction Illustrated explains that the quantity and quality of daylight in a space are determined by several factors. The size and orientation of its window openings, the transmittance of the glazing itself, and the reflectance of both room and outdoor surfaces.
So lots of variables.
Yes. For example, south-facing windows are considered ideal for daylighting if, and this is a big if, horizontal shooting devices can effectively control excessive solar radiation and glare. This prevents overheating and uncomfortable brightness while maximizing natural light, creating a truly comfortable and energy-efficient space.
It's all about thoughtful design and integration then, even down to the very materials themselves and understanding their inherent strengths and weaknesses.
Indeed. Fundamentals of Residential Construction further elaborates on wood properties, noting that hardwoods, for instance, have complex cell structures with large pores for sap transport and smaller, denser wood fibers for structural strength, as seen in a cross-section. Understanding these cellular details influences how wood is best utilized in various applications, from structural framing to fine finishing, ensuring its optimal performance and longevity. It's a deep respect for the material's biology and mechanics, really.
So, the next time you walk into a building, consider the invisible layers of science, meticulous regulation, and material intelligence that work tirelessly to keep you safe, comfortable, and well-lit. It's truly a testament to centuries of accumulated knowledge. Now, moving from these physical building blocks, let's turn to the invisible structures, the rigorous processes, meticulous planning, and collaborative spirit that bring these incredibly complex constructions to fruition.
Right, this raises an important question. How do you manage such intricate processes effectively? How do you ensure coordination and control from conception to completion? Our sources, specifically CMAA Construction Management Standards of Practice and a Guide to the Project Management Body of Knowledge, PMBO Guide, offer a comprehensive roadmap. They outline the choreography needed to turn ideas into reality.
Okay, let's start with those fundamental project management concepts from the PMBOK guide. They might sound a bit dry, like definitions, but I imagine they're the bedrock that prevents chaos in massive projects. What are some of the absolute basics?
You're right, they can sound dry, but they are the psychological and procedural bedrock. For instance, an assumption log. It's used to record all project assumptions and constraints throughout the project lifecycle.
So you write down what you're taking for granted.
Exactly. The deeper insight here is that we often proceed assuming things are true. This log makes those assumptions explicit, allowing for better risk management. Then there's authority, defined as the right to apply project resources, expend funds, make decisions, or give approvals. It clarifies who has the power to act, preventing indecision and bureaucratic paralysis.
Crucial.
Yeah. A backlog is simply an ordered list of work to be done, often seen in agile methods, indicating outstanding tasks. And a baseline is the approved version of a work product, serving as a fixed point for comparison against actual results to track performance. The deeper insight is that these seemingly simple tools ensure everyone is literally and figuratively on the same page when the inevitable challenges arise.
Those are clear definitions that create a solid foundation. It's like setting the ground rules for the entire game. Now, let's look at the broader life cycle of a construction project. How do the CMAA standards break that down from idea to finished building?
The CMAA standards detail a comprehensive project lifecycle, which is crucial for managing complexity. It starts with the pre-design phase. This is focused on project initiation and program development, essentially figuring out what needs to be built and why, laying the philosophical groundwork.
Okay, the what and why.
Then it moves into the design phase, which involves meticulous cost management, reviewing design documents for constructability, can we actually build this efficiently, and preparing bid documents. The goal here is to catch issues before they become expensive problems on site.
Foresight is key in those early stages, definitely. And then when it's time to actually select a contractor and start the physical work,
That's the bid and award phase, where bids are evaluated and contracts are executed. This requires careful scrutiny to ensure the chosen contractor can deliver on quality, schedule, and budget. The project then transitions to the intense construction phase. This includes establishing on-site facilities, managing coordination, overseeing time and cost, and handling crucial documents like requests for information, RFIs, and submittals. These are the daily communications that keep everything aligned.
the real nitty-gritty.
Yes. Finally, there's the post-construction phase, which covers acceptance and performance testing, final inspections, punch lists for remaining minor work, and producing record drawings. This ensures the building not only stands but performs as intended and provides a clear legacy for future maintenance.
That's a lot of moving parts, to say the least, like orchestrating a massive symphony. Is there a central document that ties all these phases together, a kind of conductor score?
Absolutely. A critical document identified is the Project Management Plan, or PMP. This plan, prepared by the construction manager, outlines the strategies for fulfilling the project's requirements: scope, budget, schedule, environmental conditions, basic systems. It requires owner approval and crucially serves as a measure of the team's performance, ensuring everyone is aligned with the project's objectives from the outset. It's the master plan that guides every decision and every resource.
Think of it as the ultimate choreography, where every step, every decision, from the smallest bolt to the overall budget, is meticulously planned and managed to avoid chaos and achieve a unified goal. Now, the BIM handbook highlights a major shift in how construction is managed with digital tools. How does building information modeling, or BIM, integrate with and maybe revolutionize overall project delivery?
What's fascinating here is how building information modeling, BIM, truly acts as a central nervous system for a project. It seamlessly integrates design, cost, and schedule information. It's a game changer for project coordination and efficiency because it creates a living digital twin of the building, basically.
So BIM isn't just about 3D models then. It connects to everything, a much deeper integration than just visualization.
That's a common misconception. BIM software goes far beyond visuals. It provides detailed quantity and component information. This enables vital support for many management tasks by linking design data to various systems like accounting, procurement, even payroll. This significantly reduces redundant manual data entry and all those tricky synchronization problems that used to plague large projects where information was siloed and often outdated. Everyone works from the same source of truth.
I can imagine how much time and error that saves. And what about for the people actually doing the building, like contractors and fabricators? How does BIM help them visualize and execute?
Well, for contractors, BIM offers new insights because they can leverage the graphic models to visually analyze project progress and highlight potential or existing problems before they become critical. It's like a crystal ball for construction almost. For subcontractor fabricators, the benefits are substantial across all phases: project acquisition, detailed design, including engineering and coordination, and actual fabrication. It allows them to efficiently formulate and revise design proposals and coordinate their specific systems with the overall building design, making for a much smoother, more precise process.
That sounds incredibly powerful, almost too good to be true. But are we totally rid of traditional drawings yet? And what are some of the ongoing challenges in fully adopting BIM? Because no technology is ever a perfect magic bullet, right?
Right. While BIM greatly reduces the manual effort for drawing generation, drawings themselves will continue to be required for some time due to existing contractual processes and, frankly, established work culture. It's a gradual shift. A key challenge is maintaining integrity across different design models: architectural versus structural versus construction, for example, as changes are made by respective disciplines. Current interoperability tools like Industry Foundation Classes, or IFCs, primarily support visual inspection and physical clash detection.
So they stop pipes hitting beams.
Exactly. Which is good for avoiding literal collisions. But it's not a full solution for complex performance relationships, like how a structural change impacts thermal loads.
So if a structural change impacts thermal loads, for example, that connection isn't always automatically updated across different models. That sounds like a potential Achilles heel.
Exactly. Managing those intricate performance-based changes across different systems is a recognized limitation. The future points towards smart automated transactions, implemented on BIM servers, to augment and increasingly replace manual updates. But this requires ongoing research to define complex relationships between building objects across discipline-specific systems. It's an evolving field, constantly striving for that truly seamless digital integration.
And where does the construction manager fit into this digital revolution? Are they more like a tech guru now, or still the master organizer?
The construction manager, or CM, plays a pivotal role in transitioning the model to the construction phase. They ensure proactive participation from all stakeholders: owner, designer, contractor, subcontractor, suppliers, even regulatory agencies. It's recommended to have an available on-site model and a designated BIM integrator for projects of appropriate size and complexity.
Makes sense.
The CM also encourages the use of 4D models, which integrate BIM with schedule information for time management. This allows for visual analysis of deviations from planned sequences and durations during periodic progress reviews. It makes it much easier to spot and address delays proactively. So they're still the master organizer, but now with incredibly powerful digital tools at their disposal.
Imagine building a complex structure where every bolt, every beam, every cost, and every schedule milestone is tracked and visualized in a unified digital model before a single shovel breaks ground. That's the powerful, evolving promise of BIM. But even with the best planning and technology, what happens when things inevitably go wrong or need to change? Construction Management Jumpstart and The Goal offer insights into managing these real-world challenges.
Yeah, this raises an important question about adaptability and problem-solving in construction, particularly how to maintain momentum when faced with unforeseen issues, which are frankly inevitable in any large, complex undertaking. It's about how we react when reality throws a wrench in the gears.
I've heard the term change order in construction, and it often sounds like it means delays and extra costs. What exactly does that entail, and why is it so critical to manage?
Well, Construction Management Jumpstart underscores the critical need for change orders to be properly authorized before proceeding with any changes in work. This is paramount.
Why? Just paperwork.
It's more than that. If a contractor proceeds without proper authorization, they risk not getting paid for that extra work. The process involves discovering a deficiency or a need for change. Maybe a client requests an alteration or an unforeseen condition is uncovered on site. Then an estimate of the cost is computed, which can range from a simple on-site calculation to a detailed quantity takeoff.
So it's not just about the costs of the new materials or labor, but also overhead and profit, I assume? It's like a mini project in itself?
Correct. The estimate total, including overhead and profit, is then presented in a standard change order form submitted to the architect and eventually the owner for approval. These changes may also require additional time to be added to the contract duration, so that request is made alongside the compensation request. Once approved, the document is routed back to the contractor and work can proceed. It's a formal process designed to manage risk, ensure fair compensation, and prevent small changes from spiraling into major disputes.
That's a very practical aspect of project management. But what about more systemic problems, like bottlenecks in the workflow that slow everything down? You can't just issue a change order for a slow process.
Right. This is where the goal, while ostensibly about manufacturing, offers highly relevant lessons for project delivery and construction. It introduces the concept of identifying bottlenecks within a system, for instance, specific machines or processes that limit the overall output. The key insight is that the capacity of the entire system is limited by these bottlenecks, much like a narrow section of highway dictates the speed of all traffic.
So how do you manage these bottlenecks to keep the project moving? Is it about simply pushing harder at that point?
Not necessarily pushing harder, but working smarter. The book emphasizes implementing priority systems to ensure these bottlenecks are always working on high-priority items. For example, using red tags for late orders and green for others, and then prioritizing materials with the lowest number within the same color. The goal isn't just individual efficiency, but increasing overall throughput, getting the total work through the system faster.
Ah, throughput. So the bottleneck sets the pace.
Exactly. The bottleneck becomes the drumbeat for the entire production line, or in this case, the construction project.
And sometimes, does that mean breaking traditional rules or conventions to serve the overall system?
It absolutely can. The text emphasizes that sometimes breaking established rules, such as for lunch breaks at bottleneck work centers, is necessary to increase overall throughput rather than merely focusing on individual efficiencies. The core insight is to have faith in what we know, that these bottlenecks are the critical points, and proactively manage flow rather than simply reacting to external pressure. It's about optimizing the entire system, not just its isolated parts, by understanding where the true leverage lies.
It's a reminder that even the most rigorous plans require flexibility, proactive monitoring, and a keen eye for where the actual work gets stuck to keep the entire system moving towards its objective. This deep dive reveals that building isn't just a technical endeavor, it's a deeply human one, imbued with philosophy and constantly evolving with our understanding of the world. Let's explore this broader context.
Absolutely. And what's fascinating here is the intricate intersection of ideals and practicalities that shape the built environment. Our sources offer rich perspectives on architectural vision, the moral dimensions of engineering, and how these inform the very spaces we inhabit.
Let's start with an architectural icon, Frank Lloyd Wright. What does his autobiography tell us about his approach to design and his personal philosophy? Because he certainly wasn't one to follow convention.
No, definitely not. Frank Lloyd Wright, an autobiography, though a personal account, really illuminates his architectural philosophy of organic architecture. He championed independence and self-discovery, for instance, critiquing conventional educational methods that he felt stifled creativity and independent thought.
Sounds like him.
Right. Wright defined good architecture not just aesthetically, but as an embodiment of truth and beauty, and crucially, as a direct response to the environment and human needs. He dismissed superficiality, emphasizing genuine expression. A house should grow naturally from its site and from the lives within it.
So, for Wright, a building wasn't just a structure, it was an extension of life and nature itself, a holistic creation. What impact did he believe his work could have on people?
He believed his work could inspire hope and cultivate a deeper connection with nature, fostering a sense of harmony between people and their surroundings. His vision was foundational for many who followed, proving that architecture could be a deeply personal and philosophical statement.
Shifting from architects to engineers, what's the broader ethos of that profession, according to our sources? Because it seems like the engineer often works behind the scenes, yet their impact is profound.
Samuel Florman, in The Existential Pleasures of Engineering, highlights that the engineering profession has historically been, in his words, obsessed with morality, conscience, and social responsibility, dedicating itself to service to humanity. He notes that classic definitions, like Thomas Treadgold's from way back in 1828, frame engineering as the art of directing the great sources of power in nature for the use and convenience of man. This underscores a profound ethical commitment to improving human life through practical application of knowledge.
That's a powerful and noble vision. But Florman also challenges some older, perhaps less appreciative views of practical work, doesn't he? Pushing back against the idea that thinking is superior to doing.
Indeed, he challenges the ancient Greek idea that thinking is better than doing, which often deemed handicraft arts ignoble, fit only for slaves. Florman argues that bodily immersion in some hard reality and the necessity of judgment and practical work cultivate both intellectual and what he calls sub-ethical virtues.
Sub-ethical virtues.
Yeah, meaning it fosters responsibility to external reality and shapes an educated will that moves beyond mere wants. It implies a deeper moral development through hands-on engagement. It's a powerful argument for the dignity and character-building power of engaging with the physical world.
So building things teaches us not just technical skills, but character and a profound sense of responsibility. Let's look at another historical figure, Eugene Emmanuel Viollet-le-Duc, and his thoughts on architectural progression, particularly how past styles can inform the future.
Right. Lectures on Architecture by Viollet-le-Duc provides another profound historical lens. He compared and contrasted Greek, Roman, and medieval architecture. He observed that Greek architects meticulously designed forms with the sun in mind, ensuring light and shadow played an integral role in their aesthetic.
Very thoughtful.
Yes. Conversely, he criticized Roman architecture for prioritizing magnificence over taste, often resulting in superficial ornamentation that disguised underlying structural principles. Basically, prioritizing show over genuine structure.
So the Romans were more about show, while the Greeks were more about thoughtful integration with natural forces. And how did he view medieval architecture?
Precisely. Viollet-le-Duc praised medieval architects, on the other hand, for achieving a sense of unity and repose in their interiors, contrasting it with the more varied and dynamic effects of their exteriors. Fundamentally, he believed that true innovation in art comes from paying regard solely to principles and rigorous analysis of the past, rather than mere imitation.
Learn from the principles, don't just copy the style.
Exactly. He was a strong advocate for logic and reasoning over blind tradition, a forward-looking sentiment that resonates across centuries, arguing that we learn from history to innovate, not to copy.
That's a fascinating perspective on drawing inspiration from the past without simply copying it. Now, our sources also briefly touch upon the very origins of certain modernist spatial concepts, linking them to artistic movements. Siegfried Gideon's Space, Time, and Architecture shed some light on this. What does he say about how architects like Le Corbusier were influenced?
Right, what's fascinating here is that Gideon's space-time and architecture is the closest the sources get to discussing the roots of modernism, specifically regarding these spatial conceptions. He mentions that futurism and cubism, prior to 1914, enlarged optical perception. Crucially, cubists like Bruck and Picasso quietly developed artistic means for our spatial conceptions through their still lifes.
Through still lifes.
By breaking down objects and showing multiple viewpoints simultaneously, they provided an impulse to new spatial conceptions in architecture. It changed how people saw space.
So painting and sculpture actually influenced how architects started to think about space, leading to the clean lines and open plans we associate with modernism. That's a powerful cross-pollination of ideas.
Exactly. It's a direct lineage of influence. Gideon specifically notes that Theo van Doesburg's Steel Group exhibition in Paris in 1923, designed with C. van Esteren and G. Rietveld, exerted a great influence upon the leading talents such as Le Corbusier and Mies van der Rohe.
Ah, okay. Direct influence.
Yes. And he further highlights how Frank Lloyd Wright's earlier perception of the house as a flowing space bounded by vertical and horizontal planes had been fully taken and understood by these early modernists. This demonstrates how abstract artistic movements and Wright's innovative spatial ideas directly contributed to the conceptual framework of early modern architecture, valuing open, interconnected spaces over traditional enclosed rooms.
This isn't just about constructing buildings, it's about the very act of creation, the responsibility we hold to society and the environment, and the deeply personal and collective journeys of those who shape our world. Speaking of responsibility, how are we reimagining construction to meet the critical demands of sustainability in an era of climate change?
Well, if we connect this to the bigger picture of our planet's future, sustainable construction, green building design, and delivery provides crucial insights into the evolving landscape of environmentally conscious building. This isn't just a trend, it's become a fundamental shift in how we approach construction, driven by a growing imperative to minimize environmental impact.
How exactly do we define and measure a green building today? Are there specific standards, or is it more of a loose concept?
No, it's becoming much more defined. High-performance green buildings are defined and rated by assessment systems. The most prominent in the United States are LEED Leadership in Energy and Environmental Design and also Green Globes. These systems score building projects based on a specific philosophical approach, essentially standardizing what constitutes a green building, identifying its important attributes, and measuring its performance across various categories.
What kind of categories are we talking about? Does it cover everything from energy to air quality?
Yes, it's quite comprehensive. These categories cover everything from site selection and water efficiency to energy and atmosphere, materials and resources, and indoor environmental quality. The advantage of these systems is that they provide a standardized definition, making it clear what green actually means in practice and how performance is measured. It moves beyond vague intentions to measurable outcomes.
That standardization sounds incredibly beneficial for consistency, but are there any downsides or challenges with these assessment systems? Do they ever become too rigid, maybe?
There are indeed challenges. A significant disadvantage is that each system, like LED or green globes, represents only one organization's vision of what a green building is. Another common issue is their reliance on energy modeling to forecast energy consumption, rather than using actual in-use energy data as the arbiter of success.
Ah, the prediction versus reality gap.
Exactly.
Yeah.
This can, and sometimes does, lead to discrepancies where actual energy consumption is much higher than originally forecast, which can be quite embarrassing and, well, undermines public trust.
So the models aren't always matching real-world performance, and I can imagine project teams might get so focused on getting points that they lose sight of the bigger picture.
That's another risk. There's a concern that project teams might develop what the source calls LE brain, where they focus so much on accumulating points for certification that they lose the ability to think creatively about holistic, sustainable design.
Checking boxes instead of truly innovating.
Potentially.
And how?
However, despite these challenges, significant progress is being made. The systems are evolving.
What does that progress look like? Are green building requirements starting to be integrated into broader building codes, moving beyond just voluntary certification?
Yes, and that's a crucial development, really a game changer. Standards like HHRA 189.1 2014 are specifically designed to incorporate green building requirements into mainstream building codes. The aim is to drive sustainable design into common practice for the majority of projects, not just the top 25% or so targeted by LID.
making it the norm, not the exception.
Exactly. This allows organizations like USGBC, which manages LID, to then set even higher benchmarks for genuinely high-performance buildings, continuously raising the bar for environmental responsibility.
That's a huge shift, from optional certification to code-mandated sustainability. What else is on the horizon pushing the boundaries of green building even further?
Well, the field continues to evolve rapidly. We're seeing the emergence of net zero built environment concepts, where buildings produce as much energy as they consume annually. There's also the Living Building Challenge, LBC, which sets even more stringent regenerative design standards, aiming for buildings that actually give back more to the environment than they take.
Regenerative, wow.
Yeah. And we're also seeing environmental product declarations, EPDs, which provide transparent data on the environmental impact of specific materials, like a nutrition label for building products. These mark further evolution in this critical field, pushing construction towards true ecological responsibility and transparency.
You might think of green building as an optional extra, but our sources show it's rapidly becoming an ingrained part of building codes and an essential way to measure a project's true, long-term impact on both occupants and the planet. Finally, let's zoom out to systems thinking and the very future of how cities and buildings will function in an increasingly interconnected world.
Right. This raises an important question. How do we design for a future that is inherently unpredictable? And how do we integrate technology without losing the essential human element? It's about understanding the intricate dance between parts and the whole.
Let's start with the basics of systems thinking. What exactly is a system in this context? Because it sounds like it's more than just a collection of parts.
Yeah, thinking in systems of primer introduces these core concepts. A system isn't just any collection of things, it's an interconnected set of elements, coherently organized in a way that achieves a purpose. These three things, elements, interconnections, and a function or purpose, are fundamental to understanding how anything, from an ecosystem to a complex building or a city, actually works.
Elements, interconnections, purpose. Got it. Like an orchestra.
Exactly like an orchestra. Individual musicians are elements, their sheet music and conductor are interconnections, and the purpose is to produce beautiful music. All parts must work together.
And what role do delays play in how systems behave? Because in a complex system, information flow and timing must be critical.
Oh, delays in feedback loops are critical determinants of system behavior. They often cause oscillations. Think about managing inventory. If you receive delayed information about your stock levels, you're likely to overshoot and undershoot your ordering goal, leading to cycles of too much or too little stock.
The bullwhip effect.
Precisely. The same principle applies to larger systems, like the supply and demand of electric power plants. Long construction times make it impossible to respond perfectly to rapidly changing electricity demand, leading to cycles of overcapacity and undercapacity. These delays are often invisible, but profoundly impact system stability.
That sounds like it could lead to a lot of instability, like a driver overcorrecting on the highway. Are there ways to build stability into a system to buffer against these delays and fluctuations?
Yes, large stocks, referred to as buffers relative to their flows, provide stability. The example given is a large lake versus a small river. Catastrophic river floods are more common because rivers have small stocks relative to very fast flows, making them inherently less stable.
Okay, so bigger buffers mean more stability. How does that apply to buildings or cities?
Well, in the built environment, this means that while the physical structure is crucial, it's rarely a leverage point after it's built. You can't easily change the stock once it exists. The real leverage lies in proper initial design and then in understanding its limitations and bottlenecks for maximum efficiency, rather than trying to fix it later. Designing for resilience from the start is paramount.
That's a powerful idea, designing for resilience from the start. Let's shift this systems thinking to the grand scale. How are we envisioning the future of urban landscapes with this in mind?
The City of Tomorrow explores what it calls future craft, which interestingly isn't about predicting the future, but rather about influencing it positively through provocation and open debate.
Provocation and debate. Sounds interesting.
Yeah, it's a design approach that actively engages with what could be, rather than just passively accepting what will be. It aims to shape the trajectory.
So it's about imagining possibilities to guide present actions, pushing boundaries. What kind of future does it envision for buildings themselves? Will they be static structures or something more?
It envisions dynamic spaces where buildings become intelligent agents. They gain the capacity to learn from and coexist with their occupants through sensor networks and data. This leads to a fundamental shift from merely living in a home to living with a home.
Living with a home.
Yes. Architecture, in this view, becomes a form of interface, a connective tissue between digital and physical realities. It enables spatial cybernetics, where the physical environment responds to and learns from our interactions, dynamically adapting to our needs.
That's a truly post-human concept almost, where humans and technology are inextricably linked, like our smartphones have become extensions of ourselves. It sounds like a new era of urban living.
Indeed, the text discusses a post-human entity born with technology, where human and technological systems are inextricably enmeshed, the smartphone being a prime example of this coevolution. It advocates for opening urban platforms and data to foster innovation and civic engagement, transforming cities into complex, transparent meshes where rich information promotes appropriation and experimentation by citizens.
So democratizing city data.
In a way, yes. This vision frames access to the city's information and life as a basic human right, recalling Henri Lefebvre, Le droit de la ville, or the right to the city. It's about empowering citizens with knowledge about their environment.
So it's not just about smart buildings, but smart, transparent, and accessible cities where citizens have more agency and a voice in how their urban spaces evolve.
Precisely. This evolving paradigm also challenges the traditional productive, repetitive versus intellectual, creative work divide of the industrial age. As individuals gain more agency through distributed systems and access to information, the old distinctions blur. It's about a future where technology amplifies human potential within a transparent, interconnected urban fabric, fostering creativity and collective intelligence in how we build and inhabit our world.
From understanding hidden snags in a system to imagining cities that learn and adapt, this isn't just about constructing buildings, it's about constructing our very future. One interconnected component at a time, always, hopefully, with the human element at its heart. Hashtag tag tag outro. Wow, we've covered so much ground today. I mean, from the timeless strength of a carefully chosen beam to the cutting-edge intelligence of a dynamically learning city. What an incredible journey through the intricate world of building science, project delivery, and the evolving human relationship with our built environment.
We really have. We've seen how meticulous attention to the fundamental properties of materials, like Alberti's insights on wood, still underpins all robust construction. We've explored the rigorous frameworks of modern project management and the transformative, integrative power of BIM in orchestrating increasingly complex builds.
Yeah, the BIM part was fascinating.
And we've touched upon the philosophical motivations of architects and engineers, the critical importance of sustainable practices for our planet, and the exciting, perhaps even, daunting future of smart, interconnected urban environments.
It's abundantly clear that whether you're designing a single home, managing a massive infrastructure project, or envisioning an entire urban development, every decision ripples through the entire system. This deep dive truly highlights that building is not a static act, but a continuous process of learning, adapting, and innovating, always seeking to balance human needs with environmental realities.
Indeed. And if we consider how historical figures like Viollet-le-Duc championed principles over mere imitation, or how Floorman eloquently articulated the moral significance of the engineer's work, it compels us to think critically about our own roles and responsibilities in shaping the world around us. These aren't just technical jobs, they're acts of creation and stewardship.
So here's a provocative thought for you, our listeners, to carry forward. In a world increasingly shaped by digital systems and smart technologies, where buildings are becoming intelligent agents that learn and adapt, how do we ensure that the human element, our inherent creativity, critical judgment, our deepest values, remains irrevocably at the heart of how we design, construct, and interact with our future? Can we truly live with a smart home or city and still maintain our own capacity for, well, unselfing, as Floorman put it, and deeply engaging with the physical reality we build? Or do we risk becoming passive occupants in our own creations?
Profound questions, and we've only just scratched the surface today, haven't we? There's always more to explore.
Absolutely. We hope this deep dive has given you a richer, more interconnected understanding of the incredible thought and effort that goes into shaping the physical world around us. Until next time, keep digging deeper.